Thank you. First of all, my name is written pronounced like Cemal, so I don't want anyone to know me in a wrong way. My presentation today is about some case studies and validation strategies, but rather than how validation must be, like Christopher told us, what is done in some validation of some products. This is actually some part of the work we have done in CORECLIMAX, that seeing who is doing what in their validation. And in my season, after assessing these validations, I will make a mini demo by validating HydroSap H11 product for only 1 day in Finland, and show some a basic comparison using Panoply, just only to visualize it. So let's look at our products. We have here 5 products. 4 is a snow product and 1 sea ice product. I won't go into much detail because, like I said, this is to see what is done in each product and a comparison of the methods used. Globe snow extent is already told by Kari before noon in the morning. Specifications are written here. Well, this is actually for the Northern Hemisphere, but since to compare with the other products, we will talk about only the European side of the product. The other product is Landsap snow cover. This is the part of HumanSat subnetwork, and actually on this map it's seen like there's totally and partially snow cover, but validation is done only considering like binary if there's snow or not. Another product is the H10, the snow mask of HydroSoft product. This is again a part of HumanSat sub applications. The coverage is as seen on the map, the European area, the HydroSoft area. No need for details. The other product is H12, part of again HumanSat subnetwork. The difference between H10 and H12 is the fractional snow coverage, but H10 is a snow mass. It's a binary product. This is a given in percentage, the values. And I think, resolution is the same. Last product is actually, it consists of 3 products. These are the sea ice maps done by FMI. When you go into the MyOcean catalog, you will see that this product is starting from an early date, but it's actually done by FMI lots of years ago, like 30 years maybe. But since the algorithm and the name is changed, it is they're written like a different product. It's actually not. These 3 products here are the ice concentration, ice thickness, and ice drift. The first product is a bit different because it's not an automated product. It's done by ice analysts by looking at the SAR images, but other 2 products are automated using SAR images. Validation strategies, well, let's say first, there's 2 parts in this presentation, the validation methods and strategies. Strategies are too generic to assess, so we can only look at what is done or which reference data is used. In Globe Snow, a visual inspection is used. Visual inspections are done either by looking at the satellite images or similar products if they are showing any correlation. A direct comparison with in-situ data is done by binary values and also continuous values. These 2 different values are, like Kari told us, The binary values are in the snow mass, and continuous values are the fractional snow cover. And an inter-satellite comparison is done. In this validation, there's also a comparison between two instruments is also done. Like these two instruments are AITSR and AVHRR, the old one and the new one. For Landsat products, again a visual inspection is done with satellite images. Comparison with in-situ data is included in the strategy, but it's not done as written in the validation report. I have no idea about this. A comparison with reference satellites derived data inter-comparison is done. And also, there's two versions now in this product, so also the versions are inter-compared with themselves, with each other. For H10 snow mask, well, these steps are written a bit differently because I've taken this from the reports. These are the steps decided by CEOs in the Hydrosat project. So this is like step-by-step work written like that. So it says the observation data containing snow cover measurements, in-situ data needs to be collected. The reference satellite product data needs to be collected, and they need to be checked for consistency. This consistency is about the latitude, longitude information, if they really match or there's any error or something. Because I have also seen that in that H10 product, for example, latitudes and longitudes are written not in decimal, but like 90 degrees is written like 9,000. So it needs to be scaled. For H12, again the similar steps are written. There's only one difference, and that is the E-codes regarding to the observation data. These E-codes are the classification of the snow that is seen in the observation field. So there's different methods for this, but the one used here is looking at the observation site, so deciding which classification that must be. Like, is there a 10% snow in that area or 20% in that area? So there's a table for this. So you look at the snow and decide which E-code is corresponding to that one. And for the sea ice products, all these three products are validated by direct comparison. With one is with in-situ data, one of them is model, two of them is in-situ data, and one of them is with model data. The methods and strategies, these methods are actually mathematical, statistical methods. The first one is the reality of results. So that's an objective assessment, like in the all products. For example, looking at satellite images and saying if it's reasonable or not. So this is a preliminary validation method. Numerical difference is used in CIS products mostly. If you have some continuous values, then with the reference data you can always see the difference. Either you can report all the difference or you can report the distribution of the difference. Error matrix is a basic tool used for satellite products. I will explain it in the next slides. Regression analysis is fitting a data to some line, so that seeing if it shows looking at the correlation and seeing if there's any bias or so you can also calculate the error with that, root mean square error. Trend analysis is also used in climate services to see if there's big anomalies in the changing values. And error characterization of these methods are written under. Reality of results are generally reported by comments because there's not much thing to report with numbers. Numerical difference can be shown with operational graphics. This operational graphics, I wanted to say like how many values, like what intervals are how many times seen. Any pie chart, bar chart, or something like that. Scatter box plots. This is actually also used with regression analysis, like we have seen in the Christopher's presentation. I will also show some plots. Continuous data statistics are the results like probability of detection, probability of false detection, accuracy, user's accuracy or producer's accuracy. The values are like that. And these values are generally explained in the validation reports if they are used, how to calculate them. So rather than knowing them, you can already see in the report what you are looking for, how kind of error, how kind of correlation is that. In trend analysis, there's comments, of course. This is the comparison and the table which method is used in which product. Actually, we have written error metrics for binary and some multi-category separate, but we can count them as one. So if we count them as one, we can see that in the same project, generally same methods are used. Regression analysis is always used, and it's good to have a look before validation. It is reasonable. CI's product is a bit different from this, of course. Yeah. I will skip below snow validation and turn back later. It's better to start with this because below snow doesn't have any example for visual inspection. These are the images that is used in validation for a preliminary validation. For example, like I said, it is also can be compared for other products. Like in this validation, one day here is objectively assessed with the same day of the no-IMS product, and it's also compared with the satellite images, RGB composite, or I think this is the same. Yeah, but the colors are different. So, for example, this is actually dependent on the algorithm, but I don't have any information about this. But in this picture, for example, these reds are snow. So you will take this area with your product and see if there's any snow, or it's like the inverted, or is there some anomalies. Like we said, in this product, comparison with in situ data is not done. Intercomparison is done with no IMS data. A difference about this validation is the error characterization, because the values are given in time series rather than tables. So you can also see these scores changing with days, so that you can also see if the correlation or errors are changing in the summer and winter, because snow product is actually for winter. There's not much snow in summer. Well, in Europe, let's say. And one more difference here is the classified pixels. In other products, generally they are giving only the scores and probabilities, but here's also the classified pixels. One can think that this is actually related with the instrument, but still it's a kind of score. And the other continuous statistic values used here is probability of detection, false alarm ratio, bias, proportion correct, and statistical score. And also a comparison is done at the old version. This is the second version. In H10, in HydroSat products, the main point was keeping the in-situ data large as possible. So in that map, you can see the points of the stations, the in-situ data observations. In other products, we generally see if it's done by some institute in Finland, then the in-situ data is in Finland. But here, all of the collaborating countries are given the observational data so that large statistical results can be presented. In this map, it's also the mountainous regions are also shown, but in validation, there's no difference in the method, but it's to see if in mountainous regions the correlations are different or not, because the algorithm is different in the mountainous regions. And these results are given in very large tables. This is only for one country, for Germany. Is it visible? Kind of. For flat areas and mountainous areas, the values are given in different tables, and also they are given together. This is for one country, and there's results for 8 or 9 countries in this report. So you can also see if the validation results are homogenized or not. Here are some examples for the other reference data that are used. These are used in case studies. In the HydroSat products, each collaborating country into the project has to do at least one case study for the validation. So, for example, here you see the grants that are used in Italy, or some cloud type products. This is used in the case study in Poland, for example, and for Finland, satellite images. And these case studies are done in different ways, so there's very different data, like even temperature and precipitation data is used. There is also a study with hydrological models for H12. I don't remember wrong. It's done somewhere in Turkey, and well, I don't know the details of the study, but it's mainly based on the amount of snow is correlated with the change of snow water or the water in the area. In H12, these are the codes that I was talking about. For example, you are looking at the observation site, and the ground is full with ice, and it will be 9. If it's snow, sorry, it will be 9, and it goes to 0 by decreasing. But there are some critical points, like with ice, for example. Compact or wet snow, with or without ice covering less than 1/2 of the ground. It's actually to divide it more class as possible. After doing this, this product is also can be compared, like each E-code is showing 10% snow coverage in the south, but there's many different comparisons I will show. Yeah. Another difference here is the reference data, the in-situ data used in H12 is not as wide as H10. So E-codes are here, yeah. Equals are classified like this. If it's between 1 and 5, it will be between 0% and 50%. If it's 2 and 6, it will be 50%, between 50% and 100%. And 9, 8, 7, 4, and 3 is 100%, not 0, of course. And the continuous values in H12 are also classified to 4 values, not to make this table more complex, because this continuous table for a multi-category validation, if you use more columns, more values, it will be more complex. So that is seen enough in the project. And this is reported in the validation report. So you can see here the numbers. So this side is the reference data and this is the product. So here you basically write the numbers of the correspondence, then calculate these values. The overall accuracy and RMEC are the only values you can get from this table. Instead of in the binary contingency table, like having probability of detection, bias, proportion correct, you only get these values from these tables, a multi-category table. Case studies in H12 are done in 2 countries, Finland and Turkey. These analyses cover visual inspection, inter-comparison with other satellite products in some areas, and hydrological impact study. In Finland, 2 problems about the product is seen by using these case studies. Well, of course, not all of these case studies are reported. So this is a good example for that. In the H10, there's minor problems reported with case studies, but here, like for example, in Finland, 2 studies are reported and 2 studies showing 2 problems about the product. And one of this is the misinterpreted clouds, and the other one is some geolocation errors. See the globes now. Yeah. Like I said, in globe snow, 2 instruments are used. So the reference data for these 2 are different. For AAPCR, there is much more in-situ data. And these include Finnish snow course measurements, weather station measurements, snow depth measurements in Switzerland, ESAMD data for Germany, and some snow depth on model data over Austria. And for the AVHRR, snow depth measurements in Switzerland and model data over Austria is used. Here you see the validation is, the table is for the binary continuous table. This is it. And values used are probability of detection, false alarm ratio, KIPA score, some skill score defined in the report. And again, here is the thing with the E-codes occur because this product is also covering percentage over the area, snow covered area. So again, these E-codes are used to convert the observations to numerical values, and the comparison is done the same way with H12. Because of the values are also continuous, we can have a scatter plot here, seeing if the results are correlated, and they calculate the root mean square error. Yeah. The intercomparison is done with Landsat 7010+, but it is a also for both instruments for ALTCR and AVHRR. Here on the map you see the scenes used for the intercomparison. I think they tried to be homogeneous for the matter. So selected far scenes, 13 scenes are used, and also the forest to the area, forest fraction is considered. You will remember from the morning that Curry showed the difference between the forested areas and normal areas, non-forested areas. So this is an example of operational graphics. I used the word. It also shows the forest fraction. So you can see here if the difference between the product is correlated with the forest or not. And these 13 scenes are reported with also scatter plots. You can see that there's much more data in that plot. This is for 1 day. And they calculated the root mean square error and root mean square deviation and correlation. There's also comparisons with satellite images, but these are just to help. I think after the comparison, the visual comparison, also regression analysis here is used, as you see. It's a bit small now, I cannot read, but still there's the line equation for the comparison. For AATCR, this comparison is done over Himalayas and AVHRR over European Alps, West Alps. There's also one more comparison in globe snow. They compared two sensors with each other for different vegetations. You see here the scatter plots for this comparison. So we can see that if the errors in the product is caused by the instrument or the algorithm itself. Sea ice products in my ocean catalog, the ice concentration is directly compared with the model data, the ice algorithm by University of Bremen. The only difference is calculated between two products, and this difference distribution is plotted like that. So by seeing only the minimal error is seen high, the others are low. So it shows it's working. I think because there is not much plots than that. For ice thickness, in situ measurements from the Finnish icebreakers are used. These are for this period only, of course, the positions of the icebreakers measurements. And here's the comparison with the product. Again, there's a regression analysis here. Ice drift validation is a bit different because here there's two kinds of ice drift over the sea, short and long drifts. So these short and long drifts are classified and then validated differently. And this difference is for long drifts, both the vector, the direction and the magnitude is validated, but for short drifts, the only thing is validated is the magnitude. And results are given by scatter plots. These are the scatter plots for long drifts. And that is collected by buoys on the ice. So it's in situ. Yeah, if you have any questions, I can take here, then I will make my demo after that. No? Okay. So I wanted to make this demo by one of the products that I assessed, but this is the product that I can easily access the data. So this will be a validation using contingency table with the H11 data over Finland, this area in the frame, over only 1 day. So we will see what's the difference between the validation for 1 day and all the year, for example. Here's an example of the ground data collection. In H11, also the institute data is used, and we will use institute data. This is a measurement site from Sodankylä. You see some Canadians here, but it's really, there's different techniques, of course, but these are only examples. So this ruler is for snow depth, and I'm not sure about this trash can thing, but I think it's for snow water equivalent. So these are measured every day and uploaded into some server. There's a common server, common database for that. And from that database, we download the data by some scripts. Of course, I wanted to show you or make you download this data with some scripts, but it's almost impossible. It will take too much time. So I downloaded some of this data for you. In this table, is it readable, this columns? Okay. The half of this data is downloaded and half of it is I created myself, I calculated myself. This is year, month, day, latitude, longitude, not status, snow depth, and the mean temperature is downloaded. And in an Excel table, I fixed these latitudes and longitudes according to the resolution of the product. The resolution of the product is 0.25 pixels, degrees, sorry. So with a basic equation, I converted them to these values, and also the longitude. The status value is important for us because the status shows if one is wet and 2 is dry. But this is not measured, directly measured. I mean, this also shows a problem about the snow products because you cannot directly go to site and say this is wet snow, this is dry snow. You need to touch or something. So the method used here is looking at the snow depth and the mean temperature over the day. So if it's under some degrees, it will be dry, and otherwise it will be wet. So in this script, it is written like here, if the mean temperature is under minus 1.5 degrees, it will be wet. And this condition is for the calculating mean temperature. If the number of observations in 1 day is smaller than 4, it won't be correct. So the status is calculated from the script. And here we basically directly compare the status of the product and the status of the observation, measurements. And I made here a table. So the first one is the observation data, and the second one is the product. So if the observation is dry and product is wet, we write here 1, and others are like that: dry, dry, wet, wet, and wet, dry. So we expect dry, dry, and wet, wet to be high here, if the product is correct. And here's the invalid column, and this invalid column shows if the cell in the product is cloud, water, or not classified with some instrument errors or something. Then we take these values here. By the way, you will see here like 56 values. This is only to show, so I will directly open the values here. These are the old values. And here is how many are them. So I basically wrote them here and then calculated the scores. These scores are written in the validation reports. Well, validation report of H11 is not present at the moment, but in H10 this is same. So from here we see a probability of detection, or let's look at accuracy, like 40%. This is very low. But when we do this validation over these dates, in the same day here, today is the 25th of this month, very good results. Where is the accuracy? Here, 75%. So this also shows that a validation result of whole month or whole year doesn't mean that each day it carries that accuracy. Yeah. And I have one more thing to show. The half of this is actually showed before in this workshop by using Panoply and MathCDF. But here we will make a small comparison. This is also something you can do with Panoply. If you're gonna use a data set and see if it fits with others, you don't have to look to the map in Panoply in very detail. If it works. Let's say we will use globe snow, fractional snow cover for 10th month of 2004. And the other product is MODIS data. These are monthly coverages. And this will take a time. This one. This is a big data, so it takes like 10 seconds. You can see the difference in Panoply easily. Of course, that doesn't mean that product is good, but just a preliminary validation for yourself to use on your own way. So this is the globe snow over northern hemisphere. So on this map, you can also combine this with MODIS data. Here, when you say combine plot, you will select the other product. And it directly gives the difference between these products. But here you have to take care that the values must be in the same units and same intervals. So we can see here, this is the globe snow and this is MODIS. So we can see this is percentage, we can assume, but it is also written here. You have to check here the metadata. For example, for MODIS, it shows if the value is between 0 and 100, this is the percentage, and the other values are the special occasions. So you also have to care that, for example, if there's a cloud, the difference will be over 200. So you need to eliminate that from the map. So we need to set the scale also. Yeah, the biggest difference here is 200, as we say. Let's make it, well, the other can be bigger, so like this. So normally this has to show close to white, but it doesn't show because somehow there's a problem in the data, because one of these data sets is actually not between 0 and over 200, it's starting on 20%. So there's a problem with that data set, but if you take two data sets here with the same values and same units, you will see the difference easily here. So you can also, after validation, you can also see, I mean, that data can be correct for Europe, but difference can be bigger for in Asia, for example. You can see the difference with that tool. And there's only a scaling factor here. I think this is to set the units, like if one is millimeter and one is meter, for example, we can make a 3 here and it will fit. I assume. I didn't try. Yeah. Thank you. Any questions?
Okay.
Yeah.
This is more a comment. Thank you, Cemal, for this very extensive description of snow validation. It is a tricky one. One comment more. You mentioned already that this HF product number 10 is not validated using in situ data, and the reason is that this product is defined to be a meteorological snow product, so that even the tiniest little layer of hoarfrost is considered snow. So that these automatic snow depth measurement systems do not distinguish snow when it is less than 2 centimeters. And besides that, the WMO stations, many of them do not report when there is not snow. They only report when there is snow, but when it is 0, you don't know whether it has been measured or not. So this is one tricky thing for snow validation.
Yeah. Thank you, because I think I forgot to mention that. Actually, I didn't say the institute for X10, it's for Landsat product. But this issue about not sensing, for example, you see here 3 tables for the same validation, but thresholds for the judging is different. So, like you said, you must do snow validation for different thresholds. Like here, for example, in the first one, judging the pixel as snow, if the fractional snow cover is bigger than 50%, but the second one bigger than 15%. This not only shows if the sensing sensitivity, but you can also look here for you which one is better. If you judge an area it covered as snow, if it's bigger than 50% or 15%. This is was fractional snow cover, and where is it? Yeah, I can see, but for H10, snow depth is used, so like you said, so the thresholds are like 2 centimeters, 1 centimeter, and 15 centimeter, I think. There is 3 tables, if I remember correctly.
The current definition is that also hoarfrost is considered snow, so that it is not the depth of the layer, but its radiative characteristics. Like if you now go outdoors, you see that even 2 centimeters of snow matters quite a lot from the radiation point of view, and that's why that product is called the meteorological snow product, to distinguish from the hydrological snow product, where the mass of the snow is important.
Thanks. Thank you again.
Okay, thank you.